Okay, excellent. Without any further ado, we can go ahead and get started. Good morning or good afternoon, everyone, and welcome to the 2025 Michael Wormit Award webinar. We are very excited to have the 2025 awardee Mathew Chow here with us to talk about some of his research work with NEO methods in Q-Chem. And just before we get started with that, a little bit about the award itself. The Michael Wormit Award was established to recognize excellence in the development of new methods and algorithms in electronic structure methods and the implementation of those methods in the Q-Chem Open Teamware software package. It is in memory of Dr. Michael Wormit, who made some significant contributions to the Q-Chem community and also to the field of theoretical chemistry in general. He did his MSc degree in medical physics at the University of Heidelberg. He did his PhD in 2010 in theoretical chemistry in the group of Professor Andreas Drew at the University of Frankfurt. And he did his postdoctoral training at Massey University in Auckland, New Zealand, and then returned to Andreas Drew's group later as a staff scientist in 2012, where he pursued his own research interests in addition to mentoring graduate students and Q-Chem developers. He contributed to the development of major Q-Chem features, including our tensor library, libtensor, and the ADC code as well. He was one of the two major architects of the libtensor project, and so he led a monumental effort involving a broad network of contributors over several years that eventually led to a new code with improved performance, optimal multi-core scaling, and a robust application program interface, which facilitated future scientific developments by the Q-Chem developer community, including me, actually, because I used libtensor in my PhD work when I was doing development work in Q-Chem. So his code contributions have affected me personally. And he, on March 14th in 2015, he unfortunately passed away in a tragic accident on the Cook Islands in New Zealand. And this award was established in his memory as a good friend, a fantastic colleague, a knowledgeable collaborator, and an excellent advisor. And this award has been established to recognize the best of the best within the Q-Chem developer community. So there are many previous Wormit Award webinar winners, so you can see all of them on this slide here. And then in addition to all of these folks, we have a new Wormit Award Wormit Award winner, which is Mathew Chow, who is here with us this morning again, this afternoon for those of you who are in a different time zone. And he is recognized for his many valuable contributions to the NEO code in Q-Chem. Mathew has really done a ton of work over the years with NEO methods. He did an internship at Q-Chem back in 2022. And he's contributed to PCM NEO methods, QMMM NEO methods, and a lot of the documentation that you've read in the manual related to NEO was written by Mathew, and all the sample jobs and things like that. So he's really done a great job building up the NEO infrastructure and making a lot of really valuable contributions to the Q-Chem code base. So we are very excited to have him here this morning. Here is the certificate of award that you'll be getting a physical copy of in the mail from Sarah at some point. And then he will also be giving a webinar about his work. Thank you, Mathew, for your work. And we're really excited to have you here to talk about your work with some of the NEO-DFT methods. So without any further ado, I'll go ahead and hand it over to Mathew. Thank you.
All right. Thank you so much, Shannon, for the introduction. Shannon, can you give me a thumbs up if you can see my screen? Okay, wonderful. Hi everyone. Thanks for attending my webinar and talk. And like I said, thank you, Shannon, for the really wonderful introduction. I'm really honored to be giving this talk in honor in memorial of Dr. Michael Wormit, who was an excellent Q-Chem developer, scientist, and mentor for many young researchers. Um, I guess today we'll be talking about some of the developments and some recent applications based on the neo-density functional theory framework that's actively being developed in the Professor Sharon Hammes-Schiffer's group here at Princeton University, and is continually being incorporated into Q-Chem. My goal really is to paint a broad stroke of what we can do in part due to some of the work that I've contributed over the years, and have been involved in terms of the development of code in the in Q-Chem. Sorry, it's closing chat. All right. To give sort of a very general introduction and just in general background motivation, one of the long-standing challenges in the field has always been the ability to describe nuclear quantum effects and non-Born-Oppenheimer effects not only accurately and efficiently, but in a way that's really accessible to perhaps like non-experts in the field. Um, and some of these challenges when describing nuclear quantum effects is we want a framework that's not overly specialized in a way that we want to be able to adapt it to solve a wide range of applications in chemistry and biology. Some of these nuclear quantum effects that we hope to describe include anharmonic zero-point energy. So if you take a look at the figure on the left, here we're showing the relative energies of four water isomers. And the energy ordering depends on the inclusion of anharmonic zero-point energy, and that's really a known fact. And here I'm just saying that, which I'll talk about on the next slide. The NEO method is really a nice way to do all that. Sort of include zero-point energy in a very efficient way that you can just sort of get it from doing single point energy calculations, and they don't require Hessian to calculate antiharmonic corrections. Another important nuclear quantum effect is hydrogen tunneling behavior, which has been shown to be important in many proton transfer reactions, such as melanaldehyde, which has evidence of some double wall character. And finally, a biologically relevant example of where nuclear quantum effects can play a substantial role is in this enzyme called soybean lipoxygenase, which is an enzyme that catalyzes the oxygenation of unsaturated fatty acids. And this enzyme displays a large hydrogen deuterium kinetic isotope effect around 80 at room temperature. And this can be attributed to a great extent of some hydrogen tunneling processes that's happening. And so how are we going to do this? Well, in Q-Chem, we, as in me and rest of the subgroup here in the Hammes-Schiffer group, we work on the development of the nuclear electronic orbital method or NEO method, and it's essentially a framework that treats specified nuclei, usually protons, because they exhibit the most pronounced nuclear quantum effects because they're very light, on the same level as the electrons. In the NEO framework, the system is divided into electron. In case you're unfamiliar, then in the NEO framework, the system is divided into electrons. Here, I've sort of employed a color coding scheme in red, and quantum nuclei here in purple, and as well as the classical nuclei. And so then in the neo-Hamiltonian, we include the kinetic energies of both the electrons and protons, as well as the interactions with each other, such as the electron-electron, proton-proton, and electron-proton Coulomb interactions. Just like in conventional electronic structure theory, we can solve the nuclear electronic time-independent or time-dependent Schrodinger equation using either ab initio wave function approaches, uh, or using something like dense functional theory. Um, and for my talk today, I'll mainly be focused on the aspect of density functional theory. Um, in the NEO-DFT framework, well, it's really a generalization of conventional DFT techniques to multiple types of quantum particles. And in the NEO-DFT framework, you can express the total energy functional, uh, as a function that depends on both electronic and protonic densities rho e and rho p respectively. And it can be broken down into the following energy components employing the same color scheme as the previous slide. Um, Here, what's color coded in a color other than black is showing the really important many body interactions. So in red is the electron-electron exchange correlation term, and for NEO-DFT we often choose just existing electronic functionals from single component electronic structure theory. So example like B3 lib, PBE0. Um, and we also have we also have an additional proton-proton exchange correlation term here in purple. And in practice, the proton-proton correlation is actually quite small since proton and molecular orbitals are generally quite localized. So actually, correlation between protons is often neglected. However, we often do include the proton-proton exchange terms from Hartree-Fock just to avoid issues with self-interaction. And finally, the most important part of this is the development of an electron-proton correlation energy term here in blue. And really, this requires a lot of sort of re-engineering and development of new functionals. Um, Sort of the common ones over the years include EPC 17 and EPC 17-1 and EPC 17-2, which are denoted after the year in which they were developed. These are LDA type functionals. And moving up sort of the ladder, we can get EPC 17-19, which is a GGA type functional. Um, and I'm sure for those of you attending this talk, I think you already know that, unlike ab initio wave function methods, which can be systematically improved by including sort of higher order terms, it's not so straightforward in the case of DFT. And a lot of this uncertainty really comes down to how well our EPC functionals perform for any particular application. And what I mean by this, I wanted to illustrate two sort of or preface this by using two sort of quick examples. So here in the bottom left is a table that shows the overall mean unsigned error in kcals per mole for proton affinities across a diverse set of molecules relative to some experimental value. Um, you can see that the predicted proton affinities are actually really off when you don't include EPC. And with electron-proton correlation, you get much closer to chemical accuracy. And I will also say that if you were to just do conventional electronic DFT, so non-NEO, but together with harmonic approximation, you can actually you do better than NEO DFT without EPC, but not quite as well with NEO DFT with EPC. So that's one of the advantages of NEO. And of course, you can also do this without having to do an additional like hashing calculation. You can just do these based on a NEO DFT single point energies. And on the right is a little bit more explicit example where I show actually the 0 point energy for here. This is just a phenoxyphenol. Uh, sorry, uh, sorry. Yes. So here is just the pair of phenoxyphenol reactant and transition state pairs. You can see that without EPC, you can actually get a very enormous error by factor around 3 to 4 in terms of 0 point energy, which we know is quite unacceptable. But when you include EPC, here we're using EPC 17.2. You can see that we get pretty good agreement with the numerically exact grid-based approach, which we use as our reference. So again, this is just sort of showcasing how important it is to get good electron-proton correlation. It's really the hallmark for the performance we get for NEO-DFT. This is just a quick outline of the various NEO-DFT-based approaches that are already implemented in Q-Chem. A lot of this work has been done by multiple people across many groups. Here, I'm really only listing the first citation in terms of the when the method was first introduced. And here are all some of the, I guess, the main authors involved in the implementation and development of these methods. I've also, in asterisks, listed the most recent Q-Chem developer, who's primarily the one responsible for implementing these in the current production code. Um, and like I said, NEO-DFT, which I covered before, really just comes down to the development and implementation of EPC functionals, which sort of laid the groundwork for all these other ones that are listed here. Um, I think I can mention it, sort of a subtle variant of NEO-DFT is this constrained NEO or CNEO approach, which is developed by Yang at University of Wisconsin-Madison, and which was implemented into Q-Chem by Dr. Enno Painter, who is a postdoc in the Hammes-Schiffer group. Um, you can think of CNEO as sort of an adaptation of constrained DFT, but specific to the case of NEO, where we have just multiple or a single proton being quantized. Essentially, it introduces an additional positional constraint into the Neo-Hamiltonian, and this generally has a lot of broad and interesting directions. In this case, for example, especially useful when you're doing in the context of seeing Born-Oppenheimer MD. Um, I won't really get into it too, but it's also generally useful if you want to map out a neopotential energy surface. I guess from here, if we want to describe, say, hydrogen tunneling processes, we can use the neo multi-state DFT approach, which is an analog of conventional MSDFT, which was developed by Jolly Gao at University of Minnesota, and was implemented by Chi Yu and Joseph Dickinson in the Q-Chem code. And it's essentially a multi-reference neo-DFT method that has the capacity of providing really accurate hydrogen tunneling splittings, as well as able to produce bilobal delocalized proton densities. And I guess moving on to some of the excited state methods within the NEO-DFT framework, we have the linear response NEO TD-DFT, which was primarily developed by actually Coraline in the group. This is a way for you to capture electron, proton, and mixed electron proton excitations. And another way we can sort of capture or describe NEO excited states is using the real-time NEO TD-DFT approach. And this is really the newest, I think, really the newest NEO-DFT based approach in Q-Chem, in which I in particular have spent a significant role in the development of. I'll get to this in the next slide, but this real-time NEO approach has led to a library in Q-Chem that's developed by myself, as well as Tao Li, who was a former postdoc in the group, but is now an independent faculty at University of Delaware. So this real-time NEO is where I'll be turning to next. So what is a real-time NEO approach? Well, it's a method for simulating coupled electron-proton quantum dynamical behavior. Here's a set of equations that you'd get if you substitute the NEO wave function into the time-dependent Schrodinger equation. You can then arrive at this set of coupled von Neumann equations, and I say coupled in the sense that these equations are actually coupled strongly together because they depend on both particle densities PE and PN, and they're both propagated numerically in time. And by propagating these equations, you can actually run like simulations that include electron-proton non-adiabatic effects. And I guess one of the additional bonuses of real-time NEO is not only can you run these simulations, but you can also analyze these trajectories that you get out of running simulations and plot spectra from it. So it's been shown that the electronic and vibrational spectra that you can get out from a real-time NEO trajectory can actually agree quite well with the excitations you do from running a linear response NEO calculation. So in addition to spectra, like I said, it's really designed for you to run non-equilibrium, non-Born-Oppenheimer nuclear electronic dynamics. And a sort of prototypical example we use to showcase this is in regards to this or in regards to it being applied to this molecule here on the right. This is a molecule for short, we just call it OHBA. And we oftentimes use the real-time NEO approach to simulate the dynamics of photoinduced proton transfer reaction. Here, this is signifying that we're actually inducing a excitation. We're actually supplying some sort of perturbing pulse that induces a pi to pi star excitation. And when we quantize this proton, which is between this donor and acceptor oxygen, and by integrating the couple electronic and nuclear dynamics, we can actually watch these densities evolve in time. And that's, I have a movie of that in the next slide. As I mentioned, Q-Chem's real-time NEO library called libRT-NEO was developed by myself and Tao, and it is in the development of which has enabled a lot of applications and extensions, some of which are still being developed in the group. Some of the ones I've specifically worked on include extending real-time NEO into the continuum settlement phase, or sort of like PCM. Also, to include the effects of an external molecular mechanical environment through Q-MEM approaches. And recently, there's been a lot of talented people in the group who've been working on extending this to hybrid light matter states or molecular polaritons. This is a movie that showcases exactly what I mentioned in the previous slide, where we photoexcite OHBA to some non-equilibrium excited state, and then we watch the densities evolve in time. And in this movie, you'll notice that I think it's playing. In this movie, you'll notice that the classical nuclei are actually fixed, but we do have a way of incorporating their motion as well, which I'll touch on briefly in the next slide. Um, so this sort of corresponds to, I think, the keywords that I've used when implementing the library, in terms of if you were to run a real-time NEO calculation, what keywords you would use in the input section. We can really break down real-time NEO into three sort of collective regimes, or rather just approaches. So when I guess or sometimes others refer to real-time NEO, oftentimes we're just referring to the case where the dynamics of both the electrons and the quantum nuclei are propagated by the coupled von Neumann equations. But as I alluded to in the previous slide, the classical nuclei are often fixed in their positions, and they're therefore not being propagated in time. Um, and like I said, there's a way for us to do this, and that's by um, coupling the quantum subsystem to the classical system via Ehrenfest theory. So in the real-time NEO Ehrenfest approach, um, we can have the motion of the classical nuclei follow, or at least the motion of the classical nuclei propagate on the instantaneous electron-proton vibronic surface. And this is essentially a way for us to have the classical nuclei follow Newton's equations of motion, and then also at the same time numerically integrate the quantum subsystem. Um, this is a pretty powerful technique that has really a lot of broad applications. I mean, this is really the step forward in terms of performing non-equilibrium nuclear electronic dynamics, and also in like the condensed phase, which I'll talk to next. But however, maybe sort of one underlying consequence that's maybe not apparent here is that when you're doing this real-time approach in general, propagating the electronic degrees of freedom um, together with the quantum nuclear degrees of freedom can be quite restrictive, because you're essentially forced to use a really, really small time step, because the electronic dynamics occur very, very quickly. So if you're really wanting to do, let's say, run multiple trajectories and also longer trajectories, this can be pretty cost prohibitive. And it also scales with a system size. One sort of approach that partially alleviates this problem is by using this electronic Born-Oppenheimer approach, which can also be applied to both real-time and real-time neo-Ehrenfest. Um, for processes that are known to be electronically adiabatic, we can invoke this electronic Born-Oppenheimer approximation, where in every time step of our simulation, we can essentially quench the electronic density back to its ground state. And by doing so, we can actually use an order of magnitude larger time step than we normally use over propagating both electrons and protons. Um, Maybe it's not obvious to others, but I think I should also point out that comparing the electronic Born-Oppenheimer real-time NEO-Ehrenfest approach with just a real-time NEO-Ehrenfest approach. In the electronic Born-Oppenheimer approach, we're probably in the nuclei on an average of just the proton excited states, but the ground state of the electronic surface, whereas in the Ehrenfest approach, you're probably getting on the average of both electron proton excited states. Um, uh, I mentioned before that we've played around with various different extensions of real-time NEO. And so sort of maybe work that I've done, I guess maybe some of the work that I've done was extending real-time NEO into the condensed phase. One of them is, like I said, is the Q-mem approach. In this Q-mem approach, I'm discussing this in the context of electrostatic embedding. Um, Electrostatic embedding, in case you're unfamiliar, is just including the interaction of the environmental charges into a one particle Hamiltonian. Um, in principle, we could extend this into or at some point use a polarizable force field or some polarizable embedding regime. And this really depends on the choice of external MD driver, or when it becomes available, also can be used internally within the Q-Chem. But this is also an avenue that we would like to explore in the future. Um, okay. So I spoke a little bit about how the electronic Born-Oppenheimer variant of the real-time Neo-Ehrenfest approach is a way forward for us to propagate nuclear electronic quantum dynamics in conjunction with an explicit solvent or an enzyme. But I also want to point out that really this is you might question, why don't you just do Neo Born-Oppenheimer MD, and why you have to use sort of real-time Neo approach. Um, I think it's really important I guess discuss a sort of paint this simple example. Um, I guess so. Here is just a model system of just phenol hydrogen bonded to just a single water molecule. This is in a bath of tip 3P waters, by the way. And this left plot is showing the oxygen distance between this phenol and the neighboring hydrogen bonded water, and the right is basically the distance between this hydrogen bonded water as well as the hydrogen. And really, I want to direct your attention to this blue curve. Actually, the blue curve here on the right. You can see that if you were just to do NEO Born-Oppenheimer MD, with a classical nuclear move on the electron proton vibronic ground state that's generated on the fly at each time step, the electrons and protons actually respond instantaneously. And so the consequence of doing this is you actually don't get OH vibration. And that's why in this blue curve here, the OH distance in NEO Born-Oppenheimer MD is just virtually smooth. In principle, we know that the proton has protons vibrate, and so there needs to be some way of capturing this. And so when we apply the Born-Oppenheimer real-time Neo-Ehrenfest approach, you can actually recover these oscillations where the proton's sort of moving back and forth. And really, this is capturing non-adiabatic effects because we know the proton shouldn't be responding instantaneously. And really, this is just to showcase that this is really a step forward for us. If we really wanted to simulate, do real sort of NEO calculations in solvent, or some sort of complicated environment like proteins, really, I think the Born-Oppenheimer real-time NEO approach is the way to go. I will say also, sort of as a caveat, this is still, you know, challenging in many ways because of very, technical considerations like, as a proton moves along, or this proton is displaced on a trajectory, how do you account for sort of energy conservation and where to move the proton basis function? So it is still very difficult to achieve, but this is quite promising regardless. Um, so I just showed how we could use real-time NEO to perform QMM simulations. This really is just an example of using QMM to capture explicit solvent effects in proton transfer. Once again, this is the same OHBA molecule that I showed a few slides ago, but the only difference now is that we're subjecting this to two different initial solvent configurations. Um, Here we start with the proton bonded to this donor oxygen, which I've labeled. And we photoexcite this system, and then we can essentially watch the dynamics occur. Here in both plots, I've labeled in both plots you have this blue curve. These are actually the same. This is just the trajectory you'd run if you were to do this photoexcitation in vacuum, so no solvent. Um, the dash curve is the distance between the transferring proton and the acceptor oxygen, and then the solid curve is the distance between the transferring proton and the donating oxygen. And the point where these two curves cross, that's when the OH distances are equivalent, and that's where we consider proton transfer to have occurred. And really the key takeaway here is that when we introduce solvent, depending on the starting initial configurations, you can either have a case where proton transfer, the rate of proton transfer is either slowed down, or in this case, it can be sped up. And really, this is just showing that just two different trajectories from an ensemble. And if you really wanted to capture sort of an average over the ensemble, or if you really wanted to capture an ensemble of this, one way you could do it is using sort of an implicit solvent, which we've also done in a separate study. I spoke a lot about solvent. You can also do the same real-time NEO simulations, but also in the context of a biological system. So an area that we really always want to be able to do is to simulate some sort of proton coupled electron transfer reaction or PCET in an enzyme. So that's sort of the really the end goal. And it's because a lot of these enzyme reactions, there's reason to believe that quantum nuclear effects and tunneling can play a significant role in not only the kinetics but also the thermodynamics. And this slide is really just to motivate how we can think about applying NEO to an enzyme. This enzyme, which I'll talk a little bit more on the next slide, is ribonucleotide reductase. But in the context of this slide, it's just a cool enzyme. Here on the left, we just simply use NEO-DFT to illustrate the proton density delocalization between these two tyrosines, Y731 and Y730. This geometry was taken from a single snapshot along just QMM AIMD trajectory, and then we just simply wanted to see what the proton density would look like if you were to run this with the NEO. You can see evidence of this sort of bilobal density, and this is some indication that hydrogen tunneling is occurring in this PCET process that you would normally pick up on if you were just to treat this classically. Here in the middle and as well as the right is an analogous real-time NEO Ehrenfest trajectory at the same geometry. But here we're actually showing how if you just start from one, the proton bound to sort of Y730, you can actually sort of simulate PCT reaction going from one tyrosine to the other. And this is really nice. It gives a lot of a really nice qualitative insight into what's occurring. But I think really what we also want to do is be able to quantify some of this hydrogen tunneling behavior. And that's work that we're currently doing right now, combining the QMMM with a NEO multi-state DFT dynamics, which I mentioned earlier is a way for us to capture these sort of processes. Now I will talk a little bit more about R&R, which I sort of basically previewed on the last slide, and shown that you can kind of use NEO to get at the kinetics of PCT reactions. So what is R&R? Well, ribonucleotide reductase, or R&R, is an essential enzyme that's used in or that's key for DNA synthesis and repair in many living organisms. Here it sort of catalyzes the conversion of ribonucleotides into deoxyribonucleotides via radical mechanism. And actually, this sort of radical mechanism actually requires 6 total PCT reactions across this 32 angstrom region that spans across both beta and alpha protein subunits. I really won't get into the detail of this enzyme. Rather, I really just wanted to focus your attention on one specific PCT reaction. That's the one between tyrosines Y730 and tyrosine Y731. Um, In this slide, I'm covering work that's previously been done by others in the group on this Y730 and 731 PCT reaction. And the overarching goal of this study, performed by primarily spearheaded by Clarice Reinhardt, a graduate student in the group, was that they wanted to uncover what the mechanism was like for PCT between these two tyrosines. Um, I guess the way this was done is to employ this technique called you might be familiar with it, is the Q-Mem finite temperature string method. Um, in this approach, we first use like classical MD, so no QMM, just equilibrate this system and account for sort of conformational sampling and sort of entropic effects from the solvent. And from then we can do this string approach. I won't get into details, but basically you can sort of carve out, or I guess in this example here, I'm showcasing what the QM region is like. And based on this QM region, this QM region here, it's has the two tyrosines and the nearby glutamate, which we treat it with just normal electronic DFT, and the rest of the enzyme backbone, which you really can't see, that's treated with just some electromechanical force field, specifically amber FF14SB. Um, and in this string approach, we first have to define what our reaction coordinates would be. So in this specific example, I guess our reaction coordinates is namely just oxygen, hydrogen, and oxygen distances for proton transfer. So we employed sort of reaction coordinates between this oxygen and this proton and this proton and this oxygen, as well as the oxygen just distance between the two tyrosines. And really, namely what I'm getting at is based on the reaction coordinates, you can generate an initial string that sort of then connects the reactant and product. So the reactant is where the proton is on this donor oxygen, so on Y730. The product is where the proton is bound to this acceptor oxygen on Y731. And based on this initial string, we can then perform umbrella sampling for each image. So that's what each of these circles are. Each of these represents an image along an umbrella sampling iteration. Iterations um, uh, represented by just the line connecting product and reactant. And uh, and in this umbrella sampling procedure, we apply restraints to each of these points on the reaction coordinates, and then it's an iterative procedure where we keep running, where we keep doing sampling until we converge to a minimum free energy path. And then we use sort of statistical methods to sort of unbias data, and that we generate the 2D multidimensional free energy surface, which is shown here in the middle plot. And based on these sort of umbrella sampling and unbiasing approaches, we discovered that, or at least they discovered that the mechanism for PCT is actually mediated by this nearby glutamate residue shown here on the right. I hope this free energy surface sort of paints this picture, but the glutamate residue really isn't an intermediate, but rather it's actually helping to shuttle the proton from the right to the left. And that's just really where the proton is on the glutamate is really just a point on the top of the free energy, the barrier. And this lengthy discussion is really just to motivate the next slide, which is that we took the same problem and we asked what would happen if we treated this transparent proton quantum mechanically. So here in this simple yet sort of elegant approach, we took the same umbrella sampling trajectory as we did in the previous study that was generated using electronic DFT with classical nuclei, classical proton, and along all sampling configurations, we calculate the 0-point energies from just simply doing a NEO-DFT single point calculation at every step. And I won't really talk too much about this, but basically we just applied a sort of reweighing procedure during the sampling unbiasing stage in order to obtain 2D free energy surfaces that include 0-point energy and some effect of nuclear delocalization and tunneling. We did this for two PCT mechanisms. I only spoke about this rightmost mechanism here on the right, but we also did one on the left. I won't really get into details other than say this is a PCT reaction that happened on another subunit of RNR. But really, the key takeaways from applying NEO to RNR is that um, uh, I guess when you normally include about thinking nuclear quantum effects, oftentimes you would expect the reaction free energy for a process to really go down. But in this glutamate mediated reaction here on the right, we see that this is actually a pretty abnormal case in the sense that upon proton quantization, so this is the free energy barrier you'd get from just having a classical proton, and below is the free energy barrier you get from quantizing a proton. We see that the zero point energy is actually slightly raised when the proton is for this process where the proton is actually shuttled by the glutamate. Um, and this is at first seemingly unexpected result. But what we discovered is that the zero point energy is actually higher when the proton is bound to the glutamate than it is when it's bound to the tyrosine. And this is something that that NEO was able to pick up on. Um, and conversely, here on the left, in this other PCT reaction where we don't have the nearby glutamate, um, it behaves normally like what you'd expect, where the free energy barrier would go down upon proton quantization. Um, and so I think really the key takeaway from this slide is that um, I guess nuclear quantum effects is pretty important because none of these effects you would be able to pick up just from running just classical MD. Um, Moreover, we also redid the same, I guess I forgot to mention, we also did the same reweighing procedure, but instead of using a quantum hydrogen, we did it with the quantum deuterium. And this is interesting because we show that nuclear quantum effects either raise or lower the free energy barrier, which can lead to range of possible KIEs. So in the direct case, sort of the what you normally think about when you include nuclear quantum effects, we see that we actually see a slightly normal a normal KIE of greater than unity. Whereas in the main reaction, where it's mediated by glutamate, we can see a slightly inverse KIE. So really, as a summary for just the NEO and RNR in general, this is just a nice sort of straightforward NEO DFT calculation that provided new insights into to a really complicated biological process that has I guess implications to to a lot of areas in biology. And I should also mention that this is a lot of this work, actually all of this work was enabled by code that I've added into Q-Chem. A lot of the sort of nuts and bolts of the code really enabled us to do sort of really nice calculations like this. I'm going to transition into another new application, maybe not as biologically relevant, but definitely more chemically relevant. And this really ties back to some of my earlier code contributions to Q-Chem. Namely, actually, one of my first projects in Q-Chem, and as Shannon alluded to, one of my first projects in Q-Chem was to extend the polarizable continuum model, or PCM, into the NEO framework. And really, I guess NEO-PCM and PCM are just regular PCM is really quite similar in the sense that here we actually have a molecule placed in continuum solvent, but except other than just having electronic densities, we also have electronic and proton densities that induce a charge and also can have mutual polarization in the same way you do with normal PCM. This leftmost plot is really just showing the electrostatic potential that's generated by the charge distribution at points on the cavity. And here on the right, this is an example where I show that that we can also employ the sort of clever switching algorithm called SWIG. This was originally designed by Adrian Lang and John Herbert, and is a unique implementation of Q-Chem. And we can show that in this sort of clever sort of cavity discretization approach, where you have sort of Gaussian blurring of charges and like a switching function, we can actually get really nice, smooth, monotonic decreases in energy long optimization. Same way you'd get if you're running just pure DFT optimization. And this is quite nice. And this has been quite broad. I mean, PCM as a whole has many different applications. I'm really just going to focus on one in general, and that's what I'll get to in a few slides. But before I go there, I sort of wanted to do sort of maybe a slight detour and talk a little bit about the constrained NEO or CNEO approach, which I mentioned earlier. Um, CNEO was developed, as I mentioned, by Professor Yang at UW-Madison, but was implemented in Q-Chem by Dr. Enno Painert. And this is related to the previous slide in a sense because there's been many, sometimes it's difficult because there's many sort of different combinations and permutations of NEO methods over the years, and it's sometimes difficult to know which methods have been adapted for what. I think we've done a pretty good job in the manual, and one of those developments is a combination of CNEO DFT or just CNEO in general with PCM. Um, Maybe just to sort of paint a broad overview, CNEO is actually, in principle, quite similar as just doing Neo DFT. But I guess really the key difference is that you have a constraint that you apply to the expectation value of the quantized proton or protons, which usually we choose as the constraint to be the position of the proton basis function center position, but in principle this could be anything or any other position you want. Um, and some caveats I should point out is that the CNEO DFT and NEO DFT are actually mathematically equivalent if you had a complete basis set. And so if you actually were to variationally optimize the proton basis function center, you expect both methods to end up being the same. And that's what this plot here on the right is really showing. It's trying to show the subtle distinction between just NEO and then CNEO in case you're not really familiar with it. Is that when you're not at an equilibrium geometry and you're just doing like sort of neo-SEF, where the expectation value of the proton can be is oftentimes not the same, does not have to correspond to the basis set center, whereas in CNEO we by definition force it to be. And so really this is just an HCN molecule where we're displacing the proton, or really the basis function center along an axis, and showing where the average density ends up being. But if you were to optimize it, you'd expect these peaks to be virtually overlapping. And so really this is CNEO is useful for our purposes because you get an extra degree of freedom in coordinate space for the quantum proton that you don't normally get just running Neo DFT, because in the Neo DFT approach, your Hessian just depends on the coordinates of your classical nuclei. So if you really wanted to maybe get like a like 3n-5, 3-6 sort of dimensional Hessian, you need to have the CNEO approach where you get this extended potential energy surface. All this is to motivate that we use this infrastructure to calculate PKs with NEO. And so we use PCM with CNEO in this framework. We first optimize various organic molecules in solvent, and then we did additional frequency calculations that allowed us to calculate thermodynamic quantities and allow us to compute eventually calculate PKAs in sort of a very efficient or comparably efficient manner as DFT, with the added bonus that you don't have to do any additional sort of anharmonic correction. So it's nothing like VPT2 or anything like that. And in this approach, we use the isodesmic approach, where we just use sort of a reference acid to avoid issues with solving the free energy of a proton and stuff like that. We've developed this protocol for computing delta G and eventually PKAs. Sort of try to explain this in very four simple steps. First, we for this whole set of organic molecules, we basically did a CNEO DFT solvated optimization. Here, I'm using the SMD variant of implicit solvation, which is PCM, but plus has some additional non-electrostatic terms added to it. We do this optimization in solvent. And from there, we can do sort of a CNEO DFT frequency calculation to get out what is essentially this extended CNEO Hessian that depends on both classical and quantum degrees of freedom. And so I hope this is easy to straightforward to understand. When we calculate free energies in the NEO approach, we have to be careful not to, as I mentioned before, NEO actually inherently captures inharmonic zero-point energy. So we actually need a way for us not to double count the proton ZPE. And one of the ways that we've come up with this is to construct this sort of reduced Hessian matrix from the CNEO Hessian that depends only on the classical nuclear degrees of freedom. And this basically allows us to sort of separate out what the zero-point energy contribution coming from the classical nuclei is, and then the part of that comes from the protons already baked into the NEO energy. And really running the whole frequency calculation, you can get sort of the entropic terms as well as thermal contributions. There are also taking the effects of solvent. This really here's some results for that study. We've tested this over a set of 47 organic molecules. Um, uh, these molecules we've obtained these molecules based on experimental data that's actually from the Ladle group. This is just one of the citations, but this is pulled from a few other places as well. Mainly we've benchmarked relative pKa's based on these 47 molecules in the acetonite trial. Here on the right we show cases where basically we took each of these organic molecules and then sort of calculate an average using each of them as a reference, and then calculate what the mean absolute error is in pKa units. The right two examples shows a pretty modest improvement with NEO. Actually, in these cases, it actually does sort of improve. The NEO approach actually gets better sort of relative pKs than DFT. But really, the really nice improvement is the one here on the left, where we show really kind of actually a remarkable improvement with the NEO approach. And the reason why these molecules on the left show sort of greater improvement than the ones on the right is because a lot of these involve hydrogen bonding, oftentimes between multiple quantum protons, and also has some effects of has great anharmonic effects. And really, this is just to show that I guess sort of as NEO sort of hitting the mainstream, this is a very nice and elegant and really straightforward approach for people just to run like really useful I guess calculations. Somewhat related to the previous project is a little bit of I think I can talk a little bit about the simultaneous versus stepwise new SCF approach. So this is related to the previous study because maybe it's not obvious, but a lot of these organic molecules we looked at previously often fairly large, involved multiple nuclear protons. And this can be quite expensive, especially during SDF procedure to optimize this problem. And one sort of way we can do to reduce the computational scaling, there are of course many other ways you can do this, such as like density fitting, but one of the really nice ways to do this is by employing the simultaneous SCF approach versus traditionally what we call as a stepwise approach. And for most cases, the simultaneous approach actually can reduce the computational scaling by around 50%. On the left, this is just benchmarked with the Neo-Hartree-Fock across a different range of water isomers, and just basically showing the scaling between simultaneous and stepwise, and showing that the cost savings is roughly about a half for most cases. And maybe just to further elaborate what I mean by stepwise versus simultaneous. So in a traditional stepwise approach, the NEO-SCF approach, you solve the Rolton-Hall equations sort of so you solve the electronic Rolton-Hall equation in a sort of mean field way, in the sense that the nuclear block is like frozen, right? So you converge one block and then you do the other block, and you keep doing this whole block scheme until both densities have converged. In simultaneous approach, you solve both of them sort of I guess in the dice scheme, you do sort of matrix extrapolation, interpolation for both electrons and protons at the same time. And it's not perhaps it might be a more intuitive way of solving this problem, but in some sense, too, it also requires a little bit more work. For example, we've also done this, or at least I've done this with this a GDM approach, which again is a QChem unique way of doing SCF that depends on the orbital gradient. You need both orbital gradients for both electrons and protons simultaneously. I should mention that these ones are not in italics are available in Q-Chem. And here's two illicit are in italics that are implemented, but not in the public release of Q-Chem yet. So I've also played with this sort of Newton raps or slash augmented Hessian approach, where it involves the calculating the orbital Hessian. And so in the orbital Hessian, you have to sort of mix nuclear electronic particle terms of your Hessian, which can get a little bit more involved. And also, as of Q-Chem 6.3, there's now a nice sort of robust pipeline for converging very difficult systems. And I've also adapted a similar scheme like this for NEO. And really, this available solver section is just to highlight that we have multiple ways of dealing with issues or cases where convergence can be quite difficult. And a lot of these are often and these are all essential for us to use as the problems we solve get more complicated. All right, so yeah, so I think just some sort of closing remarks. I think mainly I guess my overarching contribution of QChem is really uh, is multifaceted, but it's really comes down to two major developments. One of which is the implementation of NEO-PCM and Q-MEM approaches, to describe NEO in complex chemical environments. And also a large part of my development has been in the design and implementation of the real-time NEO library. This is in many ways still a very an ongoing area of development in the group. And I hope that, based on my work in developing this library and laying a foundation, this is an area that others in the group can continue to build off of. And hopefully it's a very intuitive way for in terms of a code design. And lastly, I spoke a little bit about my work in I guess beefing up sort of NEO SCF. This is sort of in line with a lot of other things I've done in NEO, which is just in general just tightening up sort of nuts and bolts and just doing a lot of these under the hood stuff that can enable some of these applications that I spoke about before. And all of this really is geared towards improving the usability and performance of NEO as it becomes more and more adopted by not only users but not only developers but also users. And with that, I just love to say I'm really honored to be awarded this year's Michael Wormit Award. And really, today's webinar is dedicated to commemorate the impact that Dr. Michael Wormit has had on not just a Q-Chem developer community, but also how to set example in terms of good mentoring and employing sort of state-of-the-art code design for conducting really good science. And I'd just like to thank Q-Chem for awarding me this achievement, as well as everyone in Q-Chem office and staff for the guidance during my time using Q-Chem during my PhD, as well as the mentorship I obtained during my internship a few years ago. I'd also just like to thank my advisor, Professor Sharon Hammes-Schiffer, as well as the whole Hammes-Schiffer group for the many scientific discussion and for supporting a lot of this work. And I think with that, I'd like to take a few questions.
Thank you so much, Matthew. That was a phenomenal talk. It's really exciting to see all of the work that you've been doing with all of the various the wide swath of different NEO methods that you've presented us with today. And as Matthew mentioned, if anyone wants to post questions in the chat at the bottom, or the Q&A section, I know that we're almost just about over time here, but if anyone wants to post any questions that they have, we can take a few minutes for that. Okay, well, if no one else has questions, I have one quick question. Can you talk about you mentioned this in passing, but I'm a little curious because the robust SCF stuff is something that we've been working on. Well, I say we, Kaushik has been working on in the office.
Mhm.
And so I'm curious how the Neo implementation, does that differ at all? Are there different, I know that like you've had to implement um, different solvers for Neo that are a little different than SCF. Is the
Mhm.
does the robust SCF differ any at all from?
Yeah.
Okay.
I think in terms of the overall sort of spirit of robust, where you sort of have this automatic detection of whether or not the SCF is either plateauing or is oscillating, we do a similar detection where, well, I think, as you know, I think in the robust workflow, you start with dice, and then if you have issues converging, you switch to A dice and back to dice, and eventually finishes with GDM. So in this approach, we've extended, like, this is why it's kind of important that we've also extended this to GDM as well to enable this robust workflow. But yeah, in principle, yeah, it's a very similar thing. We have this automatic detection thing for whether you have sort of instabilities. I think maybe slightly different thresholds for detecting whether or not something's oscillating or not. But I think in principle, it's a pretty seems to be a pretty uh, useful workflow, I think. Yeah.
Okay, awesome. I wasn't sure if the incorporation of the, yeah, I wasn't sure if there was anything that differed scientifically in the underlying problem that you're trying to solve that would have made the algorithm any different. But it's cool that it's adaptable like that. That's fun.
I will say, I think something I really didn't touch too much on is in general, I think Neo SCF is it can be it can definitely be a little more challenging to converge
Mhm.
than just doing normal SCF.
Yes.
And a lot of it is because the I guess the Neo landscape is sort of is very bumpy, I think, more so than just purely just non-Neo. And I think having these sort of very flexible solvers is definitely, and as you started running very complicated systems and you run into sort of convergence issues, having a robust workflow and the availability of these different solvers, it definitely provides is also, yeah, definitely very useful. But yeah, we're working on something to showcase this, but yeah, this is just, yeah,
Okay.
it's been implemented.
Awesome. That's so cool. I didn't realize that y'all had used that. So great. Um, does anyone else have questions? I'll just give it another second. Okay, well, it looks like we don't have any other questions. But congratulations again on the receiving the Michael Wormit Award. We're really pleased to have you here, and we're really excited about all of the different contributions you've made to Q-Chem over the years. It's been, gosh, it's been a while. You've been working with Q-Chem for a while now, so. But you've done some really phenomenal work, and we're really excited to recognize that. So thank you so much. Thank you for a wonderful talk. Um, and if anyone thinks of questions that they have later on, there will be a forum thread on the QChem Talk forum where you can ask any follow-up questions. Um, and thank you, everyone, and I hope you have a wonderful rest of your Thursday.